All right. Okay. Okay. So let's go to, okay. So we're going to cover a few topics today. The first is just a general kind of climatology of South Florida and tropical cyclones. Some of you guys probably already know some about that. Then we're going to talk very briefly about the 2023 season last year. Then, most importantly, the 2024 outlook. And then, what are some of the products and tropical hazards? Just kind of a refresher. There are some new ones that we're going to focus on as well for the 2024 season that you guys may not be familiar with because they are new and/or experimental. All right. So as you guys, one of the questions in the quiz was when is the most active period? I think the majority of you guys got it right. It is the period between August and basically October. Although the season technically goes from June 1st to November 30th, really the part of the activity, the vast majority of the season occurs between the months of August and October. And we'll kind of talk very briefly about why that is later. But as you can see, technically, you can have a hurricane most months, most times of the year, or not hurricane, but a tropical system, I should say. Most times of the year, it's just the conditions peak in the Atlantic basin, at least in that kind of August through October timeframe. In terms of like where things form in June and July, typically we tend to see systems form close to the U.S. Often you'll see them form in the Atlantic, just off the coast. When you have like a cold front that stalls over the Gulf Stream, which is an area of really warm water off the east coast of the U.S., and then occasionally it will actually turn in from what we call a cold core system or a frontal system into a tropical system. And we also have these messy systems that form near the Gulf of Mexico, associated with the feature in Central America called the Central American Gyre or the CAG. So if you wanted a big fancy word, the Central American Gyre is one of those things. But this year, you may have noticed we had this storm called Beryl earlier this month that actually formed in the Atlantic, and which is pretty rare for late June, early July. And that storm was exceptional for both its intensity and its location where it formed. So, but most of the storms that form in these months tend to be sloppy, as we call them. They tend to be sheared. They tend to have all their rain displaced on one side. They're not very symmetrical. They're not those, I guess, prototypical textbook hurricanes we all think of. Then we start to get to the peak of the season. You notice the colors. You notice the colors indicating the density of storms. We got some oranges and reds now showing up, whereas in the previous slide we had like blues and greens. And that just shows the activity really ramps up. You have kind of the textbook track, which are those Cape Verde storms, or Cabo Verde, if you want to be more with the Portuguese pronunciation. But anyway, so those storms that form way out in the eastern Atlantic, they track. Sometimes they impact the U.S. Sometimes they curve out to sea. Surprisingly, usually they curve out to sea. It's actually more common they curve out to sea before they reach the US than actually hit the US. A lot of us think of like the Andrew type tracks. The Irma is the kind of buzzsaw that just goes straight west. But often the conditions are such to where they actually will curve out to sea, but obviously not always. And then as we head to the late season, we start to head into kind of the fall. You see that the tracks, you lose those tracks near Africa, and you get a lot of tracks that are like centered around the Caribbean, the Atlantic, very close to the coast of Florida. And so we actually in South Florida, if I go back to the previous slide, we can get impacted by essentially two different types of tracks. The track that goes from the Atlantic, that's more common in August and September, and then the track that comes from the Caribbean, that's more common in October and November. And in terms of our history, if you look at Miami-Dade County, we've actually had 48 tropical storm hurricanes passing within 60 miles of Miami since 1865. So if you do the math, that's a little bit over 150 years. So about once every 3 years, we get either a direct hit or a very close hit to Miami. And actually, Miami is slightly less frequency than even like Broward, Monroe County, which is where the Keys are. So South Florida in general actually has one of the highest frequencies of hurricane impacts in the U.S., as we'll see later. I don't know if you can see these slides very well, but you see this is the number of hurricane strikes on the left and the number of major, which is category 3 or greater, on the right. You'll see the red colors and orange colors down here in South Florida, Miami-Dade, Monroe, Broward counties. That just indicates we're a hot spot. because, like I said, we can get hit from those two different directions. We can get hit from the mid-season storms that come straight from Africa, and we can get stood from those late season storms that curve up from the Caribbean when we get cold fronts that kind of lift them northward. And then if we look at like a more national view, this is what's known as a return period. So this is like however many years you expect to pass between when two things happen. Like you get in a car accident, it should be 6 years between every time you get in a car accident, et cetera, something like that. You'll see the reds, which indicate a shorter return period, means there's less time in between hurricane hits. You'll notice that South Florida, the Outer Banks, and like the Mississippi River Delta in Louisiana are kind of the hot spots in the U.S. coastline for the frequency of hurricane impacts. So really, we are one of the most vulnerable places in terms of climatology in the country, really. And then as we head to the next slide, here's some notable ones. Some of you that have lived here a while probably remember some of these specifically. I doubt many of you, anyone here would really remember any of the hurricanes on the left side, but they're pretty significant. But certainly some on the right side, any of you guys who are South Florida natives probably remember some of these powerful storms which hit us, hit at least South Florida, not necessarily Southeast Florida, like Irma and Ian mostly affected Southwest Florida. But still, that's technically in our area of responsibility at NWS Miami, so I included them as well. All right, so the 2023 season, it was a little bit actually above average last year, despite the fact that we had an El Nino. Spoiler alert for that last question. La Nina typically is more active than El Nino in the Atlantic. But one thing that we did notice is that the bulk of these storms were way out here in the Atlantic, and most of them went to sea. Really, Idalia was the only, which hit near the Florida Big Bend region, was the only storm that of any significance that impacted the U.S. And even it, fortunately, hit in probably one of the least populated areas of the Gulf Coast. So it was a little above average. And just to show here, the average line is this kind of light blue line here. You see the bar chart a little bit above average. There's also this thing that it's called ACE, which you may hear sometimes the meteorologists talk about. And all ACE is it just takes your max wind in the storm and sums it over the entire storm's lifetime. So bigger the ACE typically means you've had more powerful storms. Some years you have a lot of storms, but they're not very weak. They're not very strong, I mean. So you have a lot of storms, but not a lot of ACE. And other years you'll have a few big storms that last a long time that produce a lot of ACE because they're very strong. So sometimes we don't always just want to look at the number of storms. We also want to look at like how strong were they? How long did they last? Okay, so what about the 2024 season? So these were the predictions the official NOAA predictions. You may hear slightly different numbers from different sources, like Colorado State does a prediction typically. Some other agencies do them, but they're all somewhat similar. And the predictions are 70 to 25 named storms, 8 to 13 hurricanes, and 4 to 7 major hurricanes. And they gave it an 85% chance of being above normal, 10% chance of being near normal, and only a 5% chance of being below normal. And in case you're curious, what are the averages? The yellow numbers here are the averages. So 14 is the average. We're expecting probably closer to 20. Hurricanes about 7, and we're probably expecting around 10. Major hurricanes 3, we're expecting 4 to 7. So certainly above normal is everything is favored. And why is that? First, here's the name list for any of you curious, hopefully we don't have to go beyond this name list. As you guys know, if you get beyond W, we actually have a second name list now. You used to have a Greek alphabet you'd go to. And I was thinking about making that a quiz question, but it's really not that important. But now they don't do the Greek alphabet anymore. So now you actually have a second full set of names you would go to. We've already had 3, Beryl being the most significant. And so, like I said, most of the activity, we're in a little bit of a lull right now. We're probably not going to see much activity the rest of July. But obviously we expect things to ramp up as you head into August and then that peak of the season. So these are just some of the names that are on the list. And I have very bad luck with the I-name storms. The last 4 I-name storms at the offices I've worked with, I've had to do something for them. We had Isaias when I was in Mount Holly that caused quite a bit of impact. Ida has remnants, caused a lot of flooding in the Northeast. Ian, obviously 2 years ago when I was at the Miami office, impacted Southwest Florida pretty significantly. And then last year, Idalia, we didn't have many impacts, but we still had to issue tropical products. So if you want to place your bets, place the bets on Isaac somehow being impactful this year. All right, so what is needed for a tropical system to form? So the ingredients are the sea surface. Pretty much everyone knows you want hot sea surface temperatures. Kind of the magic number is around 80 degrees Fahrenheit. You want something called low vertical wind shear. What is vertical wind shear? That's just the difference in winds with height. So if you have winds coming from the east at the low levels, you have winds going from the west at high levels. Tropical systems don't like that because one of my colleagues has the analogy of like a layer cake. A tropical system works best when it's stacked vertically, when it's like straight up. If you start to tilt a layer cake, if you start to like make the top layers tilt off to the side, it's going to eventually fall over and collapse. And tropical systems don't like to be tilted. It's not very efficient for them to be tilted. So that's why they don't like vertical wind shear. They also, you need some like embryo. You need some like initial disturbance to form an area of thunderstorms usually. Most often, these are what we call tropical waves, these areas of thunderstorms that come off of Africa. That's the main source of tropical cyclones. Occasionally, like I said, you can get these frontal systems that stall over the warm waters of the Gulf Stream or the Gulf of Mexico. Occasionally, those are it, but most often it's these tropical waves coming off Africa. And then thunderstorm activity, which goes hand in hand. And you'll notice here is all the global systems, all the tracks ever. You notice there's a lot of tracks in the Western Pacific. The Western Pacific is actually the most active tropical cyclone basin in the world. There's also a lot, obviously, in the Eastern Pacific, the Atlantic, and then a few in the South Pacific and South Indian Ocean. There's also no tropical systems by the equator, which is just because there's not enough spin. You need some spin there, and something that's called the Coriolis effect makes sure you can't have really tropical systems within 5 to 10 degrees of the equator. And there's also this one system in South America that I think occurred in like the early 2000s. That's really an oddball. So it's a very unique system that was able to form near the southern coast of Brazil. So how do the sea surface temperatures look right now? So this is from a week ago when I was putting together this presentation. Red colors or warm colors indicate above normal. And you notice most of the Atlantic Ocean is indeed above normal, with the exception of maybe a handful of cool spots. But in general, the Atlantic Ocean still remains above normal. If you zoom into Florida, you'll see we're mostly oranges, which means a few degrees, somewhere like between 2 and 4 degrees Celsius above normal, which is pretty significant. Most of you guys have heard about this. We're not quite as warm as last year, but we're still very warm. Last year we had record warmth. I mean, some of the waters just off the coast of South Florida got close to 90, 95 degrees, which is terrible for wildlife, for coral reefs and stuff like that. And also, it's basically like jet fuel to tropical systems. So there's something you probably have heard called the El Nino Southern Oscillation. ENSO is what the phenomenon's called. And there's the two phases. There's the phase El Nino and La Nina, which are named because of they are based on the water temps off the coast of the country of Peru. And basically the local fishermen would notice it around Christmas time. So that's where the name comes from, for those of you who don't know. And it's mostly based on just the water temps in that region. And I'm not going to go through these flow charts in any, because they're kind of, but suffice to say, if the water is warmer, it's in that area of the equatorial Eastern Pacific, we call it El Nino. And if it's cooler, we call it La Nina. And that's the gist of it. There are some other things to take into account, like it is not just the water temps. It's actually a full circulation, so you have high and low pressures involved. But for identifying it, it's best to say it's the water temps of that specific region of the Pacific Ocean. And so what happens with El Nino? Last year, we actually had an El Nino year. It typically means more hurricanes in the Eastern Pacific due to less wind shear. And we saw that last year. I don't know if you guys remember the Pacific coast of Mexico got hammered with several storms. Hurricane Otis was one of the most quickly intensifying tropical systems of all time, hit near Acapulco and caused quite a bit of damage. Meanwhile, over the Atlantic, we typically have fewer hurricanes due to stronger vertical wind shear. So like I said, the winds just blow at different speeds from different directions at different levels of the atmosphere, and that causes these systems to tend to be weaker. Now, what happens in the opposite, La Nina, which is what we're predicting for this year? Spoiler alert. We tend to see more hurricanes in the Atlantic Ocean, and we tend to see fewer in the Eastern Pacific. And so far, even up to this point in July, we've barely seen anything in the Eastern Pacific. The Eastern Pacific has been very quiet this year, and that's usually not a good sign for the Atlantic. If you live in the Atlantic basin, you're actually hoping the East Pacific is active because it's going to steal some of that energy from the Atlantic and stuff like that. So you actually want to see more tropical systems in the East Pacific. Now, you don't want to see that if you're on like the Pacific coast of Mexico, but if you're in the Atlantic basin. So what are we forecasting this year? We're forecasting, the forecasts show a above average chance of a La Nina. You look at this this bar chart here. I circled like the peak of hurricane season here. You notice this blue bar is much higher than the red bar, which is El Nino, which you can barely see. And then this thing called gray, which is neutral, which is kind of like in between both. So you'll see, you can even see here, you see this little blue color off the coast of South America, near at the coast near the equator. That's indicating the sea surface temperatures are actually cooler than normal, which, like we said in the previous slide, means a La Nina is developing there. All right, there's also something called the Madden-Julian oscillation, not named after John Madden for any football fans, named after a scientist whose last name is Madden. And this is something that actually moves around the globe every few weeks. It's something that basically it helps generate thunderstorms, to explain it simply. And so this is kind of why we're seeing a lull right now in the Atlantic, is because A, we have a lot of Saharan dust, which you may have heard of, which tends to peak in July. And B, because we're actually in the phase of the Madden-Julian oscillation where the air is sinking. And sinking air does not produce thunderstorms. Thunderstorms want rising air. They want water to go from near the surface to that's how you can make clouds, basically. So right now we're in an area of sinking air. But as we head into July, the part of the Madden-Julian oscillation that favors the rising air is going to go into the Atlantic. And that's when we should expect to see activity start picking up. There's also something called I'm not really going to talk about the AMO, but this is just something that's been like the last 30 years. We've actually seen slightly more activity. We've been in a period of hyperactivity. And part of that's because we had this long-term oscillation. El Nino and La Nina switches every few years. This thing can last, it's a multi-decadal. It can last for 30 years at a time. We don't know when it's actually going to revert back to the inactive phase that it was in like the 70s and the 80s. But we just don't know. Unfortunately, we can't predict the multi-decadal oscillation very well. So putting it all together. So we have very warm Atlantic Ocean waters. We're transitioning into a La Nina, which favors below normal vertical wind shear. There's other favorable climatic patterns like that, like I said, that Atlantic multi-decadal oscillation. So, and like I said, during parts of the season, we're going to have those Madden-Julian upward motion pulses going through the area. So whenever those coincide with the Atlantic being in the peak of hurricane season, it's likely we're going to see our best activity. All right, so now that's a little bit of the season outlook. And now the second kind of half of the presentation or so is going to be a little bit of an explanation of both impacts of tropical cyclones, and then also what are some of the products we use to message these impacts, and what are some of the new ones too. So what kills the most? Most of you got this question right. I saw from the poll. The answer is storm surge. Kills about half of the people that die from tropical cyclones are from storm surge. Another 27% is from freshwater flooding, which is flooding from rainfall, rivers overflowing their banks, things like that. Only 8% actually die from wind, mostly from falling trees, actually. Most people don't die from their house collapsing on them, the roof. Most of the time, it's actually trees falling. There's a few that die from surf and rip currents. There's other offshore marine incidents like boats that happen to go into storms. And then only 3% die from tornadoes. Now, recently, if you just look at the last 10 years, actually a lot of people have died from rainfall. And that's mostly because we had Hurricane Harvey, which hit Houston, Hurricane Florence, which hit the Carolinas, and those kind of ran up the numbers on that a little bit. But historically, storm surge has been the main killer because it's very powerful. And then in terms of Florida, most of the fatalities are storm surge, and most of these fatalities were in Hurricane Ian a few years ago in Southwest Florida near Fort Myers and Naples. But as you can see here, we also get freshwater flooding, rip currents, wind are also other hazards that are important. What about indirect fatalities? So these are fatalities that are because of the storm, but they're not directly from the storm's meteorology. They're not from the wind, rain, water. Um, we have traffic accidents, people evacuating, post-storm heat. That's been a big problem in the Houston area. Post-Beryl, you lose power. It can be very hot. Carbon monoxide poisoning, which is usually from people that try to run generators indoors. That's a big thing. Prep cleanup, people touch live wires, things like that. Things fall on top of people. And electrocution is also a separate cause. So a lot of these things are pretty important. So just because the storm is over, you can't really relax and be like, well, we're safe, because there's a lot of these indirect accidents or indirect fatalities can happen too. So first, let's talk about wind. Wind is how we define categories. The categories of a hurricane are purely defined by wind. And these are the categories. No one needs to memorize these, but these are the broad ranges. And note, every time you see a wind, it's going to be rounded to the nearest 5. So you're never going to see a maximum sustained wind of 158 miles an hour. It'd always be either 160 or 155, as you probably have noticed. Now, one thing about the wind is that the damage actually increases exponentially. So a Cat 1 storm, it's not like a Cat 2 storm does double the damage typically of a Cat 1 storm. It does 10 times the damage. A Cat 5 does 500 times the damage of a Category 1 storm. And so major hurricanes only are about 20% of the hurricanes that hit the US are Category 3 or above. So about 1 in 5. But they account for over 4/5 of the damage. So there's a big difference from a wind standpoint between a Cat 4, Cat 5, and then a Cat 1. Now, what favors a high wind risk? So typically you want a strong storm with a low pressure. And then you want a small storm. Small storms like Hurricane Charlie, like Hurricane Michael, and I'm going to play the loop here. This is Hurricane Michael, which hit the Florida Panhandle. It was pretty tiny. If you look at it, it is not very big. If you compare it to like a Hurricane Ian or Katrina, it's pretty compact. But compact storms tend to be stronger from a wind standpoint because the difference in pressure between the center of the storm and like areas further out is greater because it's so small. And then storms that are strengthening as they approach the coast, like even if we think about Beryl last like a week or two ago when it hit Texas, it produced more damage than usually you would even see from a Category 1 because it was strengthening right as it hit the coast. Whereas conversely, a storm that's weakening, like an Idalia last year, sometimes won't even produce winds that are actually less than you would think because it's weakening. And then finally, poor building codes. Fortunately, in South Florida, post Andrew, we have some of the best building codes in the nation. But if you live in an area that has shoddy construction, has a lot of mobile homes, you're going to see more wind damage typically. Okay, one thing to note is that the strongest winds tend to be confined to something called the eye wall, which is the area of thunderstorms near the eye. So let's look at Hurricane Harvey, which hit Texas a few years ago. And I want you to notice this area of thunderstorms near the eye. You see the eye, which is the circle, and this little area of like orange and red near the eye. That's where you're going to see the winds that are close to what the people are telling you. Like if it's a Category 4 hurricane, you're not going to see Category 3 or 4 winds in those spiral bands that are far away from the center. You're not going to see in these bands like way up here. You're going to be seeing winds that are much less than that. To really experience the full force of a hurricane, you don't want to be in the eye wall because that's where the strongest winds are. And just to show here, these are the peak gusts that were measured in Harvey. And you'll notice these reds, pinks, these are gusts over 100 miles an hour. They're very confined to this narrow area near the city called Rockport, which is the city to the north of Corpus Christi on this map, where that eye wall, where that area, like I said, of those thunderstorms right next to the center go. So really, if you can avoid the eye wall, you're probably not in bad shape from a wind standpoint. But if you get in the eye wall, that's when you can see winds very strong that are going to cause major damage to buildings and really be a threat to life. So moving forward, hopefully we can move forward. There we go. So storm surge. This is the biggest killer. So what determines the water level rise or the storm surge? The intensity of the hurricane. Naturally, a stronger hurricane has stronger winds, which can push more water on shore from the ocean. The forward speed of the storm. A faster moving storm will typically produce We produce greater storm surge right at the immediate coast, but a slower moving storm can make the surge push further inland. So it's kind of a give and take. The size of the hurricane, bigger storm can kind of get more water. It's the ability to push more water. You think about your Katrina, your Ikes, these huge storms that have some famously high storm surges. They were very big. The angle of approach. If the storm is going like perpendicular to the coast, like it's crashing right into the coast, that's typically going to be the greatest storm surge. And then the width and the slope of the ocean bottom, and I'll demonstrate that with this next slide. So if you have a steep slope, like on the east coast of Florida, we actually have a very steep slope, like you see in this bottom image here, which actually helps reduce the storm surge. Southeast Florida, near Miami, is actually not very susceptible to storm surge. You can still get decent storm surge right near the beach, but typically because we have this slope where the water gets way deeper really fast as you go offshore, it actually helps us a little bit. But the west coast of Florida and like the northern Gulf Coast, Louisiana, Mississippi, the slope is much more gradual, which lets the water run up easy. The water doesn't have to like try to go over a cliff. It just can kind of gradually go up. And so they tend to be more susceptible to storm surge. You can't see the contours probably on this map here, but if you can see like the 10-foot depth contour in like the Gulf of Mexico is like way out in the Atlantic, whereas in the East Coast it's like right near the coast, which indicates that steep slope. So what are some of the impacts? So less than a foot, not a big problem. That's kind of what we get in our king tides, which we have here pretty regularly in Southeast Florida, which are just caused by the phases of the moon. They're not even caused by a tropical system. When you get over 3 feet, you start to have big beach erosion. You have roads flood. Occasionally, you can have stuff get into buildings. And over 6 feet, this is when you have problems. You start to see a lot of structural damage, severe beach erosion. And then 9 feet, a lot of buildings being destroyed. Think of Katrina. Think of your Ian. Think of things like that. And just to show, we have a sign outside of the building. I'm the guy on the right in this picture. I'm a little bit over 6 feet. I'm about 6'2". And you can see me next to this pole here where the orange starts at about 6 feet. And you can imagine a storm surge 9 feet, which is where this red starts up here, how much bigger that is than your typical human. So it really gives you some perspective to see like what kind of storm surge looks like at different levels. And it doesn't even take that much storm surge. You might say, well, I'm 6 feet tall. Why would I worry about 5 feet of water? My face will be above water. Well, the water is very powerful. It'll push you. It'll push you into things. You'll be pretty helpless. So 3 to 5 feet of moving water, you're in big trouble if you get stuck in a storm surge. You could very well, even though you may not drown initially, you may get blunt force trauma from being pushed into things. Things will be collapsing all around you. So definitely want to run away from the storm surge. And that's why you have the saying, run from the water, but hide from the wind. Because the wind, if you're in a good structure, probably won't kill you. Even in Andrew, which was a crazy storm in terms of wind damage, there weren't actually that many deaths. There were less fatalities in Andrew than Ian. And even though there were so many buildings destroyed, if you get under a mattress in an interior room, you have a decent chance of surviving even a Cat 5 wind. It'll be terrifying. It'll be the scariest night of your life, but you can survive. If you try to stay near the beach in a big storm surge event, you're not looking too good. It's a much greater chance of dying in that situation. Know your evacuation zones. Miami-Dade has these different zones depending on these little parcels of land. So if there is a storm, they'll say like, okay, we have a mandatory evacuation for zone A. We have a voluntary evacuation for zone B, etc. So it's good to know before the season starts, where do you fall in these zones? Usually the further inland you are, obviously you're going to be in a later zone, or you may not even be in a zone at all. There's some areas of Miami-Dade that hopefully will never flood from storm surge, like near where the office I'm in, where I'm currently in. But if you're near the coast, obviously you're at greater risk. Let's talk about freshwater flooding. This is the flooding that's not due to the ocean water like the storm surge is, but this is due to heavy rainfall. And the pictures here are from Hurricane Harvey, one of the most famous recent examples of this. 50 inches of rain made Houston just absolutely look like underwater. And even locally, we had this weak system in 2000 that produced pretty significant flooding over portions of the Miami area. So it doesn't take a strong storm, and a lot of times weaker storms, these sloppy storms, actually tend to be the worst for freshwater flooding. So what favors a high risk of freshwater flooding? The biggest thing is slow motion. The biggest factor is you want a storm if a storm is moving very slowly, much greater risk of flooding. The second thing is interaction with features like fronts. Basically, fronts can give these storms like a little bit of extra juice, so to speak, which can increase the rainfall intensity. And then finally, obviously, there are areas that are more susceptible to flooding than others. There are areas that are going to be near rivers, urban areas, because as we know, anyone that lives in Miami, you know, like that part of Brickell floods every time it rains heavily. Near Fort Lauderdale, Edgewater does too. Those areas where the water doesn't have anywhere to drain tend to have issues. And I'm going to play this loop of Harvey. We've already seen it from a wind standpoint, but I want you to see how slow it goes once it gets inland. So this is the 26th, the morning of the 26th of August. Now we're in the afternoon of the 26th of August. Now we're in the morning of the 27th of August. It's still just spinning there in Texas, not moving. Now we're approaching the 28th of August. We're almost 2 days after landfall at this point, and it's still just spinning in the same spot. That is bad for flooding because it's going to give you just periods of rain after rain after rain. It's not going to stop. Oops, I do not want to play that again, actually. And lastly, let's talk about tornadoes. Excuse me. I'm going to quickly drink some water, catch my breath a little bit. All right, so tornadoes tend to be in that so-called the right quadrant. So if you have a system moving to the north, they tend to occur between 11 o'clock and 4 o'clock. And if you have a system going to the west, they tend to occur between 8 o'clock and 1 o'clock. Those are the two directions we're going to get hit with the most in South Florida. So I just wanted to show you that it does depend on which way the storm is moving, which quadrant tends to be favored for tornadoes. A recent example of this is Hurricane Ian. Hurricane Ian was moving basically northward, and so we happen to be in the preferred quadrant for tornadoes. And if I skip ahead a little bit in this video, you'll see all these red boxes start to appear. Those are tornado warnings that our office issued. I actually issued a lot of them because I was working at night. You notice all these red boxes because we were in that, like I said, we were between that noon and like 4 o'clock area for this storm. And then eventually, as it gets further north, you see the stuff start to go in like Melbourne's area, Tampa's area. And so it was a classic example of a system that that we were in that right front quadrant. Oh, and I won't do this because we do have a story map that shows it, but I think it'll screw it because it'll screw up because I'm only sharing this tab, so you guys won't be able to see it. So not going to click that link. So what are some products we issue? The first thing is the cone. And of the questions that were asked before this video, this one did seem to trick a lot of people. First of all, the cone doesn't convey impacts. Don't think that just because you're outside of the cone, you're not going to see any impacts. It's purely where the center of the storm is predicted to track. So it has nothing to do with impacts. You can be in the cone and have like no impacts. Like if you're on like the west side of a system on the far edge of the cone, you may have no impacts, even if the forecast verifies perfectly down the center of the cone, which it may not. Obviously, this cone is a forecast, so it may change, but you may not have any impacts. Whereas if you're on the east side, you could be outside of the cone and you could have a lot of impacts. So that's the first thing to take into account. The second thing is the width of the cone is based on previous year track errors. So basically, like how historically has the NHC forecast been at different time periods? You'll notice in this example, the cone is very narrow for the first few days. And as you get further out in time, it gets wider. And that's because the National Hurricane Center's forecast tends to get less accurate, I should say, as you go further out in time. So the error increases. It's like your error at day 5 or day 6 is pretty big, whereas your error at day 2 or day 3 were pretty confident. So the cone is very narrow. But like I said, the cone is based purely on the past year's average error. It doesn't change in a given season with any storm. There could be certain storms where all our models that we use to forecast are all over the place. They could be, the cone is going to be the exact same size as another storm that year where the models are much more confident because the cone does not change throughout the season. It is the same. It is the same for the entire season. It only changes after the season is done when they go recalculate the errors, because obviously you got to recalculate the errors. And you can see if the forecast got better, the cone is going to shrink next year. If the forecast got worse, hopefully they get better. But if they were worse the previous season, the cone may widen a little bit the next year. But it's going to be the same in a given year. Okay, so that's the cone. There's also these things called the hurricane threats and impacts, which are very useful graphics that can kind of like highlight specifically what are your expected impacts from those 4 factors we mentioned earlier: the wind, the storm surge, the flooding, rain, and the tornado. One of the things about the wind, the NHC actually runs this ensemble of possible solutions. They don't just say, okay, we're going to do one forecast and we're just going to hope that's right. No, they actually use this fancy statistical technique where they produce all these possible forecasts with different tracks, different intensities, different speeds. And then using that, they can get actually probabilities of different winds. And these are these famous graphics, which will show you the probability of winds getting to tropical storm force, hurricane force. So these are very useful because they're not just like one number. They're not saying, okay, the wind's going to be 80 miles an hour, because that's pretty uncertain, to be honest. But these will give you a better representation. There's also, with using these, we can determine when can we expect the strong winds to start, because a lot of people, they want to make sure they're preparing, they're boarding up their windows, they're going shopping and stuff. You want to know, when are the winds going to start to pick up to the point where I need to stay indoors? Those are we can make these kind of graphics as well using those wind speed probabilities. And the wind speed probabilities and stuff are what drive the hurricane watches and warnings. So if you ever, those hurricane watches, tropical storm watches, they're all driven by the winds. Storm surge. We produce a lot of maps for storm surge. We produce the peak storm surge forecast. We produce the potential storm surge flooding map. And then we also have storm surge watches and warnings. Those are sort of new. They're only within the last, I think, 5 to 6 years. And they're different than the hurricane warnings. The hurricane warnings are for wind. The storm surge warnings are specifically for storm surge. Because storm surge is so dangerous, we decided we had to create additional products to kind of inform people about the storm surge threat. For freshwater flooding, we produced the rainfall forecast. How much rain do we expect? We produced this thing called the excessive rainfall outlook, or the ERO, which is like the probability of this rainfall causing flash flooding. Because some areas of the country, you can get 6 to 8 inches of rainfall in 12 hours and it's fine. Nothing happens. If that rain falls over the Everglades, who cares? But if you get 6 to 8 inches over downtown Miami, Brickell, Miami Beach, you're probably going to have problems. There's also the river flood outlook. If you live near rivers, we don't have a lot of rivers that are very flood prone in South Florida. But if you get up to Central Florida, like towards Orlando, that becomes much more of an issue. And like it was during Ian, for example. And then finally, what's new for this year? It used to be on the cone. If we look at this left image, they only show the tropical storm and hurricane warnings on the coast. You'll notice you see nothing inland. But really, there are warnings inland. They just weren't showing up on the map. Now they do show up on the map. Like you'll see this blue and red and stuff inland even. So that's new. It's a little noisy. Admittedly, it can be tough to read, but there is the option to toggle it on and off. So you will have the ability, if you want to, like you like the old school format that doesn't have the inland watches and warnings, you'll have that option. But at the same time, you can also see a more detailed picture. Another thing, because obviously the National Hurricane Center has responsibility for the entire Atlantic Basin, the majority of the countries in the Atlantic Basin actually don't speak, English is not the primary language. So now, it used to be that the San Juan office had to translate the products manually, but now there's a special AI translation, which has been trained by native Spanish speakers to produce pretty accurate translations of NHC products, so they can do them very quickly. you don't have to wait for San Juan, and you don't have to basically waste San Juan's time having to do their time to do this stuff. You can get these translations out instantly, which is very useful for a lot of the basin. So that's going to be a new thing going forward. There's additional things like it used to, like all sorts of products now. They will have this disclaimer at the bottom because there are some errors in any kind of AI translation. There's going to be awkward words, and for anyone that speaks Spanish, you'll know that what certain words for certain things in various countries will differ between one country to the other. So someone from Cuba may not be happy with the translation that someone from Mexico. You know how it is. So, but that is just things to take into account. And then finally, NHC is very active on social media. I do recommend you follow them. Facebook, Twitter, YouTube. As you might know, the U.S. government doesn't really like TikToks, so sorry, no TikToks at the moment. And they'll stream live during these events on Facebook and YouTube. We do that too. We also do Facebook, Twitter. We have a web page, and these are for your local impacts. These are some of the tweets we've done in the past. So we tend to get pretty active on social media for these events. And thank you. And that's my basic questions. Here's my contact info and the office's contact info. And I will, I guess, keep sharing, but or maybe if you want me to stop sharing, I can. But I'll mute, and you can ask any questions you guys have.
Thank you, Nick. Oh, my brain is full. Great presentations. So if you have any questions, you can put in the chat, or you can unmute yourself. So we have time for some questions.
So it's during the Niña that you have the larger amount of storms?
Yes, that is correct. In the Atlantic Basin, historically, you have more activity during La Nina. Yep.
Yes, Joy?
Yes, yep.
Yeah, can you also do bulletins using AI in French and Creole for the Creole-speaking nations?
Great question. And that is something we're actually working on. The thing with the AI stuff is you need humans that obviously speak the language to train the AI, basically to say, okay, here's your first guess the AI did. Oh, the AI said something stupid here. It used the word chispa for sprinkles for like light rain. We don't want to say chispa. That doesn't make any sense. We want to say lluvia ligera. That's a Spanish example. So we can do that for other languages too. The problem is we're just now getting in contact with people that know meteorology, so they know the right words to kind of say that speak those other languages. Because like you said, especially Creole, French for Haiti, and some of those other island nations is very important. So that is a step, and hopefully in future years we'll be able to have those products for those nations as well, because we know it's a good service to them to have stuff in their native language, so they don't have to go translate this back and forth, and it could just be an issue. But good question.
Nick, I have a question here. How do you gather your statistics on how many people are injured by trees before and during and after hurricanes?
Sorry, could you repeat the question?
Yeah, you mentioned many people get injured by trees during the hurricane. So how you get that information from?
Oh, yes. Okay, so after the storm, typically every NWS office will go out and we'll do surveys. We'll see, like, because fatalities are very important to us. We want to know, did people die? Why did they die? How did they die? Because we want to know, okay, can we do something better? Did we not forecast? Did we not message it right? So we'll go out to the communities and we'll get that information. Sometimes the media will tell us. The media often, I mean, it's kind of morbid, but the media does like to focus on deaths. They'll say like, okay, we had X so-and-so died in a tree, but we want to get all this information. We want to know who died, not necessarily who, their name specifically, but how old were they? Where did they live? What community? Because we want to know what can we do in the future to prevent these deaths. So we do a lot of effort after the storm to try to figure out, did people die? Were there injuries? Why did these people die? Could they have evacuated? Did they stay in a mobile home? Was it just bad luck? Sometimes a tree falls and unfortunately it's just bad luck. There's nothing you really could have done. So those are things we really try to do after the storm. It's one of our big tasks.
All right. Any other question? We have a few minutes.
Yes, after the hurricanes, we noticed that after Hurricane Andrew, there were a lot of like severe lightning storms, and some people got hurt from the lightning. Is that something that happens commonly after a storm?
That's a good question. So during storms themselves, tropical systems usually actually don't have a lot of lightning compared to like your thunderstorms you get on a typical summer day in South Florida. So that's actually kind of interesting. A lot of people, when you see like a movie with tropical systems, there'll often be a lot of lightning because lightning is dramatic. It looks good in movies, but typically during the storm, there's a lot of lightning. But after the storm, like you said, you can get a situation where a storm goes by and then a few days later, you have your typical afternoon thunderstorms that we get almost every day here in South Florida in the summer. They start happening, and their homes may be destroyed. They may not have any shelter. And then in that case, they are more susceptible to being struck by lightning. So it is true that after a storm, if there's been a lot of damage to homes, people don't have good shelter, they are more vulnerable to lightning. But during a storm, typically most strong storms like in Andrew, like in Irma and Ian, they're not going to have that much lightning in the actual storm. Maybe a little bit in the eye wall. If it's strengthening really quickly, you can have lightning suns. But actually, tropical systems, because the fact they're what we call warm core systems, and I won't get into that because it's not super important. They tend to actually not have that much lightning, which is kind of surprises some people because we think of lightning as being something that, every strong storm has lightning, but hurricanes actually have a lot less lightning than people would expect.
Interesting. I noticed that because I was a trauma nurse at Jackson in the neurosurgical ICU. And after Andrew, there were a lot of patients that came in with trauma that they fell off the roof because they got struck by lightning.
Oh, interesting. Did not know about that. That is good information.
All right. Any other question? Well, thank you a lot, Nick. Was amazing information. I don't know if it's possible to have a copy of your presentation, maybe.
Yes, I can email you a copy in like PDF form. And there's also even some extra slides I didn't get to because it was, but I'll send you guys the whole presentation.
Thank you. Thank you. Can you stop sharing 1 second? Great. So let's post or launch the post one. Hopefully everybody will have a 100%.
You guys did pretty good on the pre-one. There was just one question that I think the majority of you guys got wrong, but other than that, 3 of the 4 questions you guys had mostly right.
Maybe too easy.
Yeah, I should ask questions about the Madden-Julian oscillation. That's this group seems to. Well, I can tell which question is the hardest for sure, based on the fact the responses are almost even. And that was the question, by the way, to give you a hint, was the one that most people got wrong on the first one. The other ones looks like you guys got it pretty good, at least from what I can see. Can
you touch a little bit again about that? That's very important.
Yeah. So the cone, the spoiler, the cone will be the same through the entire season. So it's never going to change in size depending on what the storm is because it's based on the error of previous years. It's not based on the error of any given storm. So it's only based on the previous year's average error. So the cone will be the same the entire season. The size of the cone is not going to change depending on the storm. it'll change. Like if you look at like the day 5 forecast, like the forecast 5 days from now, it's going to be bigger than the day 1 forecast. And that's just because the average error at 5 days is bigger than the average error at 1 day. But if you look at like Beryl versus, let's say, the I-named storm, the cone is going to be the exact same size at day 5 for Beryl as it was at day 5 for the, So that's the one question that's it's tough, because really, should they have made the cone like that when they invented the cone? Probably not, because it confuses a lot of people. It even confuses meteorologists. I've seen meteorologists on TV get it wrong before. So if they could redo it, if they could recreate the cone, maybe they would not do that. But unfortunately, that's what it is. It's going to be the same with every storm through the year.
Great. So the answer would be false, correct?
Correct. The answer to that one is false. And the other ones you all got pretty much almost 100, or at least 80%. So those are all right.
Great. All right, guys. So finally, we have good news for the